One of the more difficult concepts in this chapter is using logarithmic differentiation. So students have a hard time with this a lot of times. What I want you to think about this is it's a way for us to take a complicated function. In this case, I have a pretty complicated function. I have a quotient. This one is raised to a power. This one is raised to a power of 1/2. And I'm going to use the properties of logarithms to my advantage. Okay? And so rather than just take this as a quotient rule, which I could do, in some cases the quotient rule would be easier. In some cases logarithmic differentiation is easier. So it kind of depends on the complexity of the function. But we're going to practice it on this one. This one, it could go either way. But we're going to practice logarithmic differentiation on this function anyway. And so what we're going to do is we're going to take the logarithm of both sides. So I basically take the natural log of the entire left side, the natural log of the entire right side. So I have the natural log of y on the left, and over here on the right, once I take the natural log of that whole side, now I can expand that expression using the properties of logarithms. Now I could take the derivative with respect to x of this entire thing, so the left and the right side. And here I get y prime over y. It's just like u prime over u. Here I get the derivative of x minus 2 is 1, so it's 1 over x minus 2 with that coefficient of 2 gives me a 2 in the numerator, minus the 1/2 gives me this 2 in the denominator, and u prime over u is 2x over x squared plus 1. So I'm pretty close. I have y prime. That is dy dx, right? The y prime represents dy dx. So I'm going to solve for y prime by multiplying both sides by y. And then I'm going to substitute the original expression, or the original expression for y here. That was x minus 2 all squared over the square root of x squared plus 1. So I'm multiplying it there. And now I have to multiply this in and simplify. So from here it's just an algebra problem. Right. When I do that, take a look at what happens here. I have x minus 2 cancels one of these x minus 2's. I have x squared plus 1 to the first power times x squared plus 1 to the 1/2 power. So I add those exponents. I get x squared plus 1 to the 3/2. This x minus 2 I've written here. And this I've just distributed this negative, so I get minus x squared. So 2x squared minus x squared is x squared. Negative times a negative is 2x, so it's plus 2x plus 2. So that is dy dx. dy dx is just y prime, so there's my derivative. All right, again, for an example like this, it's hard to say. We'd have to try it. Do this using the quotient rule. It would work out that way too. It might be a comparable amount of work, but the more complicated this expression gets, the more advantage there is to using logarithmic differentiation. Right. So again, the reason for doing this is just taking advantage of the properties of logarithms and allowing us to expand that out before we take the derivative, rather than using a really complicated quotient rule, or even sometimes it's a combination of quotient rule and product rule and chain rule and all those put together at once. Alright, so we're going to go back and take a look at kind of a chapter 3 example of finding the relative extrema, except now we're going to find the relative extrema of this function, natural log of x squared plus 2x plus 3. So we know how to find the relative extrema. We want to set the first derivative equal to 0, or find where it does not exist, and then show that f prime goes from positive to negative, or negative to positive. If it goes from positive to negative, we have a relative maximum. If it goes from negative to positive, then we have a relative minimum. Right? Oh, sorry. I'm writing down and you can't even see what's going on there.
Please pardon the interruption. Please release all legacies, managers, honor guards, band members, and cheerleaders at this time to prepare for the pep rally. That's please release all legacies, managers, honor guards, band members, and cheerleaders at this time to prepare for the pep rally. If they are taking a test, taken a quiz, please hold them until they have completed their test or quiz. Thank you.
Okay, so the way that we find this relative extreme is the same way we did in chapter 3. It's just that now we have a new type of function that we can perform that on. So we're going to find y prime. So I say, okay, well, I take the derivative of this. It's u prime over u. So the derivative of this inner part here is 2x plus 2, and the original u is x squared plus 2x plus 3. Now I want to know when that derivative is equal to 0. That means I just set the numerator equal to 0. I've done that over here. 2x plus 2 equals 0 means that x equals negative 1. So I make a table. I have x equals negative 1. I have values that are less than negative 1. I have values that are greater than negative 1. And I can just pick a test value and see what the derivative is going to be. Here my test value is negative 2. When I plug in negative 2, I get a negative first derivative. In the interval from negative 1 to infinity, I use a test value of 0, and I found a positive first derivative. So f goes from increasing to decreasing, and so I have a negative first derivative going to a positive first derivative, which means I have a relative minimum, because I'm going from f prime negative to f prime positive. Right, so the applications that we can use from chapter 3 are exactly the same. It's just the mechanics of actually finding the derivative have changed a little bit since we have a new type of function to differentiate.